Today's notes are over ideal gas law. Our objective, we will predict or determine or find the number of moles of a gas using the ideal gas law. Ideal gas law, the equation is PV equals nRT. Pressure is represented by P. It can be an ATM. mmHg, which is also known as torr, or it can be in kilopascals. ATM is atmospheres, millimeters, mercury, torr, kilopascal. Volume is represented by V. It has to be in liters. Number of moles is represented by N. It will be MOL. Now the gas constant is our new one. It's R. And it changes depending on the pressure. So if it's in kPa, we will be using 8.31. If it's in ATM, and I'm talking about the pressure. Pressure in ATM, 0.0821. If it's in torr or mmHg, 62.4, 62.4. Lastly, it's temperature. Temperature, T, has to be in Kelvin. That's my ideal gas law. Now, what is an ideal gas? Well, an ideal gas is a gas that behaves perfectly. An ideal gas has no attraction between the molecules. It has no size. It's negligible. It moves in a straight line, and it has perfectly elastic collisions. So when they collide, it doesn't stay stuck, it bounces right off. So is it ideal? Yes or no? Molecules of this substance bounce off each other and don't change shape or energy. Ideal. Reason being, it has an elastic collision, it doesn't stick, it bounces off, and it doesn't change at all. 2. Molecules of the substance hit the walls of the container and smash, losing kinetic energy. That is not a perfectly elastic collision because it lost energy. So that means it's a real gas. Molecules of the substance move slowly to their size, and the size of their container. Remember, it has no size and it's ideal, so that means it's real. So, when the pressure, temperature, and volume of a container are known, the moles can be, the ideal gas constant can be used to calculate the number of moles of the gas, or the ideal gas law, I guess. PV nRT. Okay, I have 4 moles in of a gas at a pressure, P, and a volume, V. What is the temperature, T? When you have a PV nRT question, you have only one set of gas variables. You have moles as well. You're going to set up a chart. P is 5.6, V is 12, N is 4. We don't know T, we don't know R. But I do know pressure. Pressure is in ATM, so my R is based off of ATM, which makes it 0.0821. Remember, when pressure is in ATM, R is 0.0821. I'm using PV equals nRT. I plug in my values. 5.6 times 12 equals 4 times 0.0821 times temperature. We're going to do the easy stuff first. 5.6 times 12, 67.2 equals 4 4 times 0.0821, 0.3284 t. I'm trying to isolate for t. So t needs to be by itself. We have to divide. Will we divide by 67.2 or 0.3284? We'll divide by 0.3284 because it's on the same side as the t. So I plug in 67.2 divided by 0.3284. Temperature will equal 204. And what's the unit for temperature? Actually, 204.6. Kelvin, it's always Kelvin. We're going to skip to number 3 because I want to make sure we understand this. We're using PV equals nRT. I'm going to quickly go through and annotate. I see that I'm in, I don't know what my pressure is. We're going to say pressure will be in ATM. Plug in, I don't know pressure. Do you know volume? I know moles. I know it's going to be 0.0821 because my pressure is in ATM. And finally, I know I'm in 400 Kelvin. So I multiply 3 times 0.0821 times 400. 98.52 equals P times 60. I'm trying to isolate for P, so what will I divide by? If you said 60, you are correct because we want to isolate P, so we have to get rid of the number attached to P. So I look at 98.52 divided by 60, and I get that 1.64, and this is an ATM is my